Whoa, yes, welcome back to Barley and Hops. Yeah, I'm George. I'm measuring the ceiling because I need the appropriate headroom in order to run this 26-gallon still with the 4-inch bubble plates. We're going to do that today. Now that everybody's back with us, yes, I've already made the measurement, okay? I've got 78 inches from the floor to the ceiling, and that is like 198 centimeters. I need, if I'm going to use all 6 of these when I get this column assembled, I actually need 218 centimeters or 86 inches, and I just don't have that right here. Of course, we've got a recessed ceiling in another portion of the shop, but we're not there for a couple of different reasons. I've got some other projects going on. So we're reduced to using only 4 of these bubble plates, but it's going to work exactly the same way. Would it work better with 6? Well, yeah, sure. It would work even better with 10. But of course, there comes a point of no return or no value added. You know, when you're purifying your alcohol from your wash. So let's just leave it at, we've got 4, and the only reason we have 4 is because when I put this together, I've got 73 inches, and that's like 185 centimeters. Is 73 inches tall, and I've got just a little bit of space left over at the top so that I don't bounce up against the ceiling. Okay, so that's why we're doing the 4 as opposed to the 6. Now, in preparation for this, I've got these are the bubble plates. They're actually the perforated copper plates, and they've got the long downcomer that goes in, that's on those. And they're just as effective, just as efficient as the multiple downcomers on the bubble plates that you've seen in previous videos. We've got some, we're gonna run those at some point in time, but I'm gonna run them with the equipment that was provided with the still. Now this is the 26-gallon 4-inch bubble plate, 6-section copper still from Milehi. Oh, what an amazing piece of equipment. Now, you'll notice how clean this one is as opposed to this one. You could probably see that from there. There is a definite difference in the two, and that's because I use that 551 cleaning solution. What is that, you ask? I knew it was coming up. Hey, and oh, by the way, the guy in the back, that guy, yeah, wake up. You're going to miss something important, and then you're going to wonder why. Norm, I know you're out there. Norm, wake him up. Thanks. I use 551 cleaning solution. We've gone through this several times. And what that is 500 milliliters of water, plain and simple, 50 milliliters of hydrogen peroxide, that's the 3% solution. You can get that at any local Walmart, CVS pharmacy, Walgreens, or any service area that you go to pick up first aid equipment or cleaning equipment in a lot of cases. And we also use 1 weight ounce of citric acid. And you can get the citric acid at your local, any area in your supermarket that may have canning equipment, or you can just order it online, but we use 1 ounce of that. So that's the basic mixture, and it'll clean copper, it'll clean stainless steel, it'll clean just about anything. All you have to do is let it sit in there and soak. It's really good for your copper mesh, copper pennies, copper saddles, stainless steel mesh, stainless steel saddles. I mean, anything that you want to just get the grime off of it, just allow it to sit in there. Now, of course, I know that someone's going to write in, and that's quite all right. I know I'm using milliliters and then ounces. I'm using 2 different scales. Yeah, that's because really 551 is really easy to remember. 500, 50, and 1 ounce. A 1 ounce is 28.3 grams. So it just sounds a whole lot better than saying 55, 23 or 28.3. 551. So, and if you're going to make a larger batch, yes, of course, go 1,102. You can scale it up if you like. Okay. Now, when we put this thing together, remember there's 2 ways to do this. Of course, there is a right way, and then there is the other way. Food for thought. The first thing that goes on here, of course, is going to be the gasket. and then a bubble plate. And yes, the bubble plates go on the bottom, and there's a reason for that, and I'm not going to put you through the pain and agony of watching me assemble this whole thing, but this is a good time to mention why the bubble plates go on the bottom and not on the top of the columns. That's because the next column, the piece that goes on, of course, will go on top of the bubble plate. So the bubble plate will be here, but it will be left open here. And that is so that the very last piece, the very last column connection you make will be the deflagmator. And your deflagmator goes on top of that. Now, why is there not a bubble plate here? Well, just think about this. If you had a bubble plate here, what would happen inside your deflagmator? Let's put this deflagmator right here. If you can slide, there you go, you can get it on there so it will actually go on. In a lot of cases it won't, but there. If we put that deflagmator there and we started to operate this deflagmator and we were condensing all of that liquid that was coming up, the vapors that were coming up, and we're condensing them so that they drop back down, where do they land? They land on that bubble plate, and then they start to fill your deflagmator. So your deflagmator efficiency drops by at least 50% because what you're doing is you're actually filling the deflagmator with a whole bunch of liquid that's being bubbled. And what you want is you want vapor flowing through here, and you want to condense it so it drops back out. That's why there's no bubble plate at the very top. Make sense? Very good. I knew you'd get that. You'd get that right away as soon as I use the deflagmator as an example. So I'm going to put this together, and I'll just start stacking my column piece by piece. Now these only need to be finger tight, and I make them pretty snug finger tight. I'll put another gasket, and then for those, now someone wrote in, and I did take it to heart. You are correct. I had every one of these in the back, the downcomers in the back, kind of in line, and it's probably not the most efficient way to do this. So I'm going to offset these, one on one side, and then the next one will go on the other side, and then on the other side, all the way up until I get to the top. And additionally, for whoever it was, several, these gaskets are not poison, okay? I know for some people that may be a surprise, but somebody spent an awful lot of time, a couple of people, an awful lot of time, and an awful lot of energy trying to debate whether, under operation in a still, whether the poison leaks out of these gaskets. It just amazes me. I just can't see how someone would design, a company would go through the research, development, and design and figure that at the very end we're going to add poison gaskets just to screw with people. All right. Enough about that. Well, we're getting close, and you'll notice that I've got my lines already on here. Now, I've got the valve at the very top. Let's talk about that briefly. There's two ways you can hook this up. You can put the in line at the top and the exit port at the bottom, or in this particular case, since it's such a short path, I like to put it in at the bottom and out the top, and that way I can control the flow a whole lot easier, because remember what I'll do is it'll go in here, it'll fill up. And then on this exit port, if I close the exit port, I can stop the water flow, or I can control how much water goes in by how much water I allow to exit. Now, this is an important function of a reflux still, because what we want to do is we want to control the temperature and the condensing that takes place here prior to my vapors that I will allow to pass at some point to continue through to my main condenser. So this one will be controlled. My main condenser will just run full bore, and all I want it to do is to condense. But this one I want to be able to control, so I've got this valve here, and that's the purpose of that valve. Now, could I put the valve on the bottom? Absolutely. Now, but why didn't I do that? Well, if your water flow goes in the top in this particular case, and your outflow is equal to your input, what happens? Well, your chamber never really fills up. You see my point? And so you're kind of losing a little bit of efficiency in your deflagmator because you're never really filling it up. You're actually outflow, your input and your output are just about equal depending on what type of a pump you have and what kind of a water source you're using. So to ensure that I get to use the entire value of my deflagmator, the water goes in the bottom and that way it fills up and then it exits. So I know that I'm using the full capacity of the deflagmator. That's the only reason. Now that I've got the cap attached, and this is the top, and you'll notice we've got a thermometer right here. We always say that you place a thermometer at the point of no return, and that's where your vapors exit your system. And in that particular case, it's directly above the deflagmator. What would happen if my thermometer was any lower? Well, I would know what the temperature is of my vapors and or liquid, but I would never know what is exiting my deflagmator. I want to be able to control that. So that's where the valve comes in handy, so that I can track the temperature of the vapors that are in this cone and that transfer across this line arm. And now they've designed this line arm to have about a 3-degree slope, which is pretty much standard so that you can take advantage of gravity in the first place, but that way it flows right back down into the area where we're going to attach our condenser. Plain and simple. Well, there, now we've got our shotgun condenser, which is a multiple tubes that run through this 2-inch pipe. And of course, water goes in the bottom and comes out the top. Now, there's 2 reasons for that. First, it's the right way to do it because your water flow should always be opposite in your final condensing, should always be opposite the flow of the vapor. And your flow of your vapor should be this direction, so your flow of your cooling water should be in that direction. That's one reason. The second reason is what I described earlier, is that, let's say for instance, your water was going in the top and coming out the bottom. Well, if your water flow was such that your input and your output were equal, well then your condenser would never really fill up and you would never be really using the full capacity of your condenser. So if you go in the bottom, it would fill up and then exit, so you're guaranteed to use the full capacity of your condenser. So that's just a good reason why it goes in the bottom and comes out the top. It just kind of makes sense. Now, this is a piece of extension that I'm really, really impressed with, and that's that cone in the bottom here. And it has a vent pipe on it, and that vent pipe is to prevent a vapor lock from taking place. So you have to have a vent in order to allow that the liquid that does condense, as it starts to collect, it'll flow. And this is probably the most ingenious piece that I am really, really happy with, and that is the parrot that is permanently attached to the still itself. Permanently affixed. And on the bottom there's a valve. You just turn this valve and you can empty the parrot, so that way you don't have to connect or disconnect the parrot during your run. You can make your run when you make your cuts. You can initially your first 4 shots, you can just open up the parrot and dump everything and then close the valve and allow that parrot to fill back up. So that is really all there is to it about the assembly. Now with the water flow, you have a couple of options at this point. Now, I know that you're familiar with the water chiller that I use, and I've got a 5,000 BTU air conditioner with the evaporator bent down that I've been using for a couple of years now. That thing works extremely well. And I've got that mounted on top of a water cooler, or an actual just a cooler, and I just pump water from that in through my system and back to and I just let that dump right back across the evaporator coil, so it chills the water before the water is again drawn back through the pump and back through. So now you'll see how I've got this set up, where I've got the water source located several feet away from the still itself. And I put a small elbow here on the bottom, and that's my water source into my Blickman Riptide pump. Now, thanks to Mike from Florida, he had 2 of them and he sent one to me, and I really like this because it's a really powerful pump. And it has actually a control valve here. You can open this valve and you can control the amount of flow that goes through your exit port. So when I turn this on, I'll have that valve turned all the way open because, of course, the valve I'm going to use to control water flow is located right here, and that's the one right next to, right on the deflagrator itself. I don't need a water flow control valve for my main condenser. I'm just going to let that run full blast because there's no need to control that at all. And the way we get there is through this Y connector. And I just, from my exit port into the splitter, and because I'm looking for laminar flow, I've got this Y connector. A T connection would work, but to me, you just don't have the laminar flow you do when you have a splitter that is a Y connection. So that's the only reason I can use actually just one pump, and I'll have two exit ports, two exits going back into the cooler, and that will run right across the evaporator coil. And then evaporator coil will cool that water, of course, and it goes right back into the system, and it's just drawn out the bottom, and it's pushed right back through the system. So therefore, I don't have to worry about ice, and I can maintain the proper temperature, which is really anything below like 70 degrees is the right temperature. The lower you get it, the longer the water lasts. It doesn't improve anything in the product just because you get it down to chilled 40 degrees. You don't need to get that low. Anything below 70 degrees is really good. Okay. Well, well, I guess not the last step, but the next step in this process is we've already done the water test. I've turned the water pump on and I've run it through, and none of my lines are leaking. Everything is going well. It goes in the bottom, goes out the top, goes in the bottom, comes out the top, and both of those go back to the reservoir. Okay. So all of that's working well. Now comes to the point of heating this up, and we're using a 5500 watt heater element in the base of this kettle, and then from there that's plugged into my 30 amp control box. Now this Milehi makes these, and they're absolutely wonderful. This is a variable control. They use a potentiometer, and they have an amp meter output, so you can visually see how many amps you're running through it. So it goes from minimum to maximum. I'll show you that. And inside here we have a 30 amp main breaker, and I've got this already plugged in where I have the other main breaker. So is it redundant? Yeah, kind of, but oh, that's fine. And of course we're in the AC variable control module, and we use this is the potentiometer used in order to control that, to control the flow of current through this system. So that means that this 5500 watt element, I can control that all the way back to about 1000 watt element, or off all the way up to a 5500 watt element. So I don't necessarily have to have full power all the time. What are we going to do? Yes, we're going to adjust this so that we've got the appropriate amount of energy going in as we are transferring out of the column in order to maintain the temperature. So let me show you this close up. So you'll see here, this is the main power disconnect. And this is, again, it's a redundant switch, but that's quite all right. Now that the power is on, that means that the system is only energized if the main power button is turned on. And once we turn that on, you'll notice that it comes on immediately. I've got it set down to minimum, actually off. There should be nothing running through it now. And as I start to turn that dial up, you may start to notice, yeah, those are the amps. And I'm starting to increase. I've got 10.7, 10.8 amps that are running through the 5500 watt element right now. And I can adjust that. And so that's how we're going to run this through its entire process. So I'll just close that box up. So for all practical purposes now, I've got water flow that I haven't started yet because my still hasn't heated up yet. I'm just now starting to heat that. So I've got water, I've got my mash inside my kettle, and in this particular case we have just at about 15 gallons. I've got my heat control going on. So all we have to do now is wait for this thing to heat up. So what are we waiting on, or how are we going to track this? There's two ways to actually run a reflux still, and both of them are correct. They just happen to be two different techniques. The first technique is to run it with the water flow turned off completely so that you bypass the deflagrator and you don't use that at all. And then you run that all the way up until you get to your proper operating temperature, which is somewhere in the neighborhood of like 173 to 176 degrees. And once that vapor comes across and starts to be produced, what are we running this as at that point? Yeah, we're running it as a pot still because we are negating or we are eliminating by not using the deflagrator. And then once you start to get product produced and you pull off your heads, then you can increase your water flow and then start to fill your sight glasses or your bubble plates with the liquid. And that will happen because in this particular chamber right here, any of the vapors that rise, that are vapor, will condense here and drop back down. And then they'll start that vicious cycle. So it will take a certain amount of temperamental balance in order for you to get the proper balance between what is cycling, as in reflux, and what is escaping, as in pure vapor. Now, that may be a technique that you like to use, and that's quite all right because it works. The only downfall, it's not really a downfall, but you have to understand going in that you're going to produce a little bit first, and then you're going to work at it backwards. And you're going to balance your power, you're going to balance your water flow in order to get your proper output. Now, the other technique is to turn this water flow on full at the very beginning, and as this starts to heat up, and your temperature will not rise because anything that makes it to your deflagrator will in fact condense. And as it condenses, it'll start to drop back down and it'll fill up all your bubble plates. Now you allow those to fill up and start to bubble because what you're doing is, we call this stacking the column, okay? So we stack the column with as much vapor that is being purified and refluxed as we possibly can, and then we start to back off the water flow, which really only heats up your deflagrator. You see where I'm going with that? It's, instead of it being super cool, now it's only cool enough to condense partially the vapors that make it here, and the remainder of the vapors exit through your column and into your condenser. And those are your most pure volatile substances, being ethanol. So that's just the other technique. So you've got two methods. You can either run it as a pot still first and then introduce your reflux column, or you can run it from the very beginning as a full reflux, and then once you stack the column, you'll start to reduce the reflux in the chamber. Stick with us as we get this thing hopping, and it starts to hopping and popping, and we're going to show you what the sight glasses look like. And it's an amazing thing to actually sit back and know that you fully understand what is going on inside each one of these sections, and then what's coming out. It's just, it's a phenomenal, it's just amazing. That's all I can say. Happy distilling.